So here's the synthesis problem. If you just want to make the molecules, remember we have to make those 4 classes of molecules. If you just want to make the molecules, here's what you got to do. Molecules that compose living systems almost always show homochirality, meaning that they have one-handedness, not the other. The vast majority of biological molecules, except for very small ones like water and acetic acid, anything larger than that, they're mirror images, just like your left hand and your right hand are mirror images. They're non-superimposable. You can't put a left-handed glove on your right hand. It doesn't fit. All molecules are like that in biology. That is hard to make. It is very hard to make just one mirror image of a compound. It can be done, but it's very hard. So that's part of the problem. When you're building molecular systems, constant redesigns are needed to take the synthesis back to step 1. So that take the synthesis back to step 1. So in other words, when you're going and you're making something, you're like, oh boy, those conditions didn't work. My stuff decomposed. So you go back to step 1 and you bring through more starting material. And so you take small amounts. You try this, you try this. Anything that would be happening in a prebiotic earth, it's marching along trying to make something. If it makes a mistake, you can't pull that entity off. Very hard to pull the entity off. Once it's on there, it's on there. So you've been going along, say, for 400 million years, if you want to take these sorts of numbers, and all of a sudden it's put a wrong moiety on there. Uh-oh, what am I going to do? Well, you got to go back to step 1. I got to go back 400 million years? Yeah, you got to go back there. Well, I don't know how to go back. Well, why not? Because I never kept a laboratory notebook. When you don't keep a record of it, you don't even know how to go back. You don't even know what you're going toward. Because it doesn't know that it's moving toward life. Remember, molecules have no brain. They don't know where they're going. That's the synthesis problem. And they don't know how to stop the course of progression or why to stop. There's no target. They don't know. I think we'll form life today. I think we'll make a certain cell. You don't know that. Molecules don't know that. So they're going along and chemical reactions are happening. It doesn't have a target. When you're in the lab, you're going toward a particular target. You know where you're headed. Here it doesn't know when to stop or how to stop. Maybe it's made a carbohydrate. It doesn't say, well, I made a carbohydrate. I think I'll stop synthesizing. No, it'll go on and make something else from that. It doesn't know how to stop. Time, although claimed to be the great savior of abiogenesis, that's before there's biology, abiogenesis can actually be the enemy. For example, carbohydrates are kinetic products. They undergo caramelization or the Cannizzaro reaction. They decompose. So in other words, when you make a carbohydrate, that is not the final product that would form in that reaction mixture. You have to stop the reaction. So a chemist watches the reaction and they stop it at a certain time to stop that progression of the molecule going on. If this is just undirected, unguided, it keeps going to other garbage. Carbohydrates are kinetic products, meaning that they caramelize, they polymerize into a bunch of trash. Just like when you take sugar and you heat the thing up on the oven and things turns into caramel, that's what happens to carbohydrates. They don't stay nice, simple carbohydrates. They end up actually dehydrating. A prebiotic system doesn't have the ability to easily purify the structures. You have to be able to purify, because if you cannot purify, then the byproducts build up in the system and they start using up your starting material and they start inhibiting the reactions that you want. You have to be able to do purification. Without purification, you can't work. Every chemist has to run a reaction, then you stop, you purify, you get it pure, and you go on the next step. Once in a while, if it's a really pure reaction, you can go on 1 or 2 steps, but you have to purify. Reagent order is essential, reagent addition order. You can't just say all the reagents mixed together and you get what you got. You're making a cake, you got your flour, you got your milk, you got your eggs. You say, well, I think I'll just add the frosting now. No, there's an order to this. This is real. This is what you do in chemistry. Things have to be added at certain times. You can't just add it whenever you want to. Reagent addition order at proper timing is critical. The parameters for temperature, pressure, solvent, light, no light, pH, atmospheric gases have to be carefully controlled in order to build complex molecular structure. There's no way around it. This is what's needed. You have to have characterization at each step. This is hard to do. Chemists have to characterize things at each step because you have to make sure what you've got before you can go on to the next step. How does nature characterize? Well, right now, biological systems characterize things by every time it makes something, there's an enzyme that checks that structure. If it's not the right structure, there are other enzymes that come and chop that up into smaller pieces and try rebuilding it again. You get a mistake in the DNA. You have enzymes that run up and down the DNA, find this mistake, excise it, and then stick in the right base there. But in a pre-biological world, there are no enzymes. How does it check it? And every time, whatever it's using to check it, whatever system is needed to check it, is more complex than the system that it's checking. So where'd you get that from? Nobody knows. Everybody's clueless on this, but nobody wants to admit it. There's the mass transfer problem. This seems like not a problem to you, but let me tell you something. This is the killer of it all. Are there any synthetic organic chemists in here? Any synthetic chemists here? Any synthetic chemists? Get your hand up high. One there. Okay. So and one there. Okay. If I say something that's not true, I want you to stand up and just say liar. All right? If I say something that's not true, just stand up. All right? Because I want these people to know, for all they know, I'm lying. You have to verify on this. All right, the mass transfer problem. Anybody who's done complex organic synthesis, what you do is you start with like a half a kilo of material, and you go along, and your yields are never 100%. You're purifying, you're going, and you end up with 2 milligrams, and you're not at your target yet. So what do? Then you go back to the beginning, and you make more, and you follow the defined route that you had defined before, and so now you can keep your yields higher, but you keep having to go back and pull up starting material from the rear. You're bringing up more material. How do you do that? So say in nature they started, say somehow it started and it got a kilo of formaldehyde and acetone, and it's going to start combining these. So these are going to go along and start reacting. At some point it's going to run out of material. How do you go back to the beginning and get more? Again, you never kept a laboratory notebook, so you never know how you got there. So even if you could repeat it, go down the same junky path and you'd run out again. You'd never get to where you want to go. Nature keeps no laboratory notebook. Next slide.